Good afternoon, everybody. It's our last day together. So we're going to do some final exam review. But I have a question for you first. In my other section, they still had some questions about Chapter 9 homework, and they kind of wanted to see some of those problems done too, in addition to the problems I selected for final exam review. Since y'all are here first, you get to decide the fate of the class. Do you want to go over, I think there's like maybe 2 or 3 Chapter 9 questions from Mastering Chemistry first, and then do final exam review? Or do you just want to skip to the exam review? You can let me know in the chat. Okay, so we'll do a couple of problems from the Chapter 9 homework, and then we will move on to the review. So for the final exam review portion, I chose some questions from the exam review that I posted, and then I also have a couple of new questions that you'll only get if you look at the notes and you're in class today. So these are problem types that you'll see on the final exam that you'll have an advantage on because you're here. I always try to make it worth it to come to class if you choose to. So this question is one that is usually a little bit more difficult, but it involves a couple of topics that we've covered in the past. When an electric current is passed through water, hydrogen and oxygen gases are liberated. What STP volume of oxygen gas is obtained from the electrolysis of 90 milliliters of water? This does not have a chemical equation associated with it, but you're told what that reaction is in the text. You have a current pass through water, and you make hydrogen and oxygen gases. All of that is your chemical reaction. So to write this, we've got water. Electric current is not any kind of a chemical compound. So we'll just write it here. We add current. And we make hydrogen gas and oxygen gas. So the first step to this problem, you have to write a balanced chemical equation. Now, so far we've written a chemical equation, but it's not balanced. On the reactant side, we've got 2 hydrogens and 1 water. On the product side, we've got 2 of each element. Not balanced. We'll start with the oxygen, because that currently is the only one that looks like it's unbalanced. So that means we put a 2 in front of the water, which is on the reactant side. Now we check and see what happened. So putting a 2 in front of that water means that we now have 4 hydrogens and 2 oxygens. Product side, we didn't do anything to it, so we've got 2 and 2. Now the hydrogen is out of balance. We're going to place a 2 in front of the hydrogen gas. And that should be the last thing that we need to do to balance this equation. So now we've done that. We have a balanced chemical equation. Let's go back to the problem. We have to figure out the STP volume of oxygen gas that we get from 90 milliliters of water. Now, we haven't done anything where you have to figure out taking a liquid volume, but there's one thing that we know from chapter 2 about water. We can use the density of water to figure out what the mass is of 90 milliliters. So that's the second part. The density of water is 1 gram per milliliter. So if you have 90 milliliters of water, you get 1 gram for every 1 milliliter. Now we can figure out what kind of problem we have. We have 90 grams of water, and we have to figure out a volume of a gas. That makes this a mass to volume question. So we haven't even done the stoichiometry part yet, but there are a few things that you needed to do before you could really get started on this problem. And the biggest issue that most people had was they didn't realize where you can get the chemical equation from and that you have to balance that. So this type of a problem is absolutely fair game for the final exam because it takes multiple, topics from multiple chapters and puts them together. We did equations in chapter 7, and then density was chapter 2, and chapter 9 is stoichiometry. So I'm hitting 3 chapters in one question. So hopefully, does this make sense so far? Because I know this one was a tough one. So now that we know what type of problem we have and we have a balanced chemical equation, we can move on and just do the stoichiometry. I'll write out the plan first. We start with grams of water. We always have to get to moles as our first action. And the way we go from grams to moles is molar mass. So we'll use 18.02 for the molar mass of water. And if you need help figuring out those, how to calculate the molar mass, let me know after class. The next step in these stoichiometry problems is to use a mole-mole ratio. It's in the form of B over A. The B is the one that we don't know. We're trying to figure out how much oxygen gas we're making. A is the one that we have some information about. Then we have to get to liters of oxygen gas, so some kind of volume. This requires molar volume because we're at STP. And at those conditions, 1 mole of oxygen gas has a volume of 22.4 liters. We'll use that unit equation to write a unit factor to convert from moles of oxygen to liters. Now let's actually put the numbers in. We've got 90 grams of water to start with. We'll handle converting to moles first. Then we have to write out the mole-mole ratio. You have to go to the chemical equation for that. The number of moles of oxygen gas we get from the chemical equation, 1 mole. Same thing for the water. You go to the equation. There's 2 moles of water. That's our mole-mole ratio. The last piece, we have to get from moles of oxygen to liters. That means from our unit equation, we've got to put 1 mole on the bottom. That means it will cancel out, and 22.4 liters of oxygen at the top. Make sure that your units cancel. That's why it's always good to write a plan, because you know what units you're looking for when you set this up. All that checks out. When you put it into your calculator, it doesn't hurt to use parentheses here. And that should be your final answer. 55.9 liters of oxygen gas. So what we'll do after each problem is I'll linger for about 10 seconds. And in that time, if you have a question, go ahead and ask it. Or if you're like in the middle of typing it out, you're like, oh, this is a long question, you can just raise your hand, throw a flag on the play, and I'll know that you have a question and I'll hold up. Otherwise, after 10 seconds, I'll just move on to the next problem. That way, you don't have to be like, oh, is nobody else going to say no questions? All right, no, we're good. So we can get through all the questions, because this is more of a watch, maybe take notes, and just let it sink in type of lecture. So if anybody has any opposition to that, let me know if you have a better plan. But that's the one that seems to work for this style of lecture. So I'll linger for a few more seconds, let it sink in, and then we'll move on to the next question. Absolutely, I'm recording this. So the YouTube video will be up and the notes will be posted today right after class. We should end class a little early, so I'm going to do it during that time. Let's move on to the next question. We're still in homework land. This time, we have a mass-to-mass question. How many grams of calcium hydroxide must react to give 1.59 grams of calcium phosphate? So that's what we're starting with. This is what we're trying to figure out. We know about a mass. The question is about a mass. Great. And there's an equation down here. Smooth sailing, right? Not quite. You always have to check to make sure that this equation is balanced. And this one is not. So your first step needs to be balancing the equation. Whenever you're given an equation, whether it's mastering chemistry or from me, check it. Make sure that it's balanced. Do you guys want me to go through all of the balancing to show you how to do it? Or do you want me to just write in the coefficients? Okay, I'll go through it. It's not going to take that long. So I'll try to do kind of the abbreviated, but you'll see all the notes of how to do it. Try to make everybody happy, which is not easy to do. Okay. So as usual, you've got to take a lay of the land. See what you have and how much on both sides. You can keep your ions together, the phosphate, which is PO4, and the hydroxide, which is OH. So that's what we have so far. First thing I'm going to do is balance this calcium. Then we make another little chart to see what the damage is. What else have we changed? So we've changed the number of hydroxides. Now we've got 3 times 2, which gives us 6 hydroxides. We didn't do anything to the product side, so you can just copy that from our last chart. Since we made a change to those hydroxides, we should fix it. That means we're putting a 6 in front of the compound that has hydroxide in it on the product side. That's the sodium hydroxide. So you place a 6 there, and you inspect to see what you've done. Since we put a 6 here, we know that we've made some changes on the product side, but we haven't changed anything on the reactant side, so I can just copy that straight over. Now I'll be a little bit more careful here. I now have 6 sodiums because of that 6 in front of the sodium hydroxide. And 6 hydroxides. We're getting there. Last thing that we have to do to balance this thing is place a 2 in front of the sodium phosphate. And that should handle both the sodium and the phosphate to balance it out. So now we're balanced. Once you have that balanced equation, you can write out the actual equation, because you can use your balanced equation to write your mole to mole ratio. So I'll write out our plan real quick up here. We're starting with grams of calcium phosphate. We're going to use the molar mass to get to moles. Then we have to get to moles of calcium hydroxide. That's a mole-mole ratio, where we do the B over A. So I'm going to kind of do shorthand here. The calcium hydroxide over the calcium phosphate. Then we need to get to grams of calcium hydroxide. Again, molar mass comes into play. When you write out all your numbers for your equation, this is what it looks like. This problem is a little bit of a pain because you're writing out such a long formula in comparison to what we normally do. So this one probably takes me the longest to write out of all the questions that we do. But I want to show solidarity. If this is what I want to see on your exams, this is what I have to show you. So you don't feel too alone. You don't feel like you're doing all the work. Hopefully you feel like I'm putting in some work too. So that's our mole-mole ratio. Remember that you get that from the equation. There's no coefficient in front of the calcium phosphate, so we wrote that as 1 on the bottom. And the calcium hydroxide has a 3 in front of it. So we write 3 moles for that, and it's on top. And after 3 years, and you've written out your equation, now, always make sure that you have the right units. It would be a shame to go through all that and you flopped something around to where you wrote one thing on top when it should be on the bottom. So always double check your units. Make sure that you meet each unit that you're supposed to in your plan. Then you can do the calculation. So that is the molar mass of calcium hydroxide. I didn't show you how I calculated that, but yeah. So that's how you can put it into your calculator. and that's the answer. So in mastering chemistry, everybody gets different numbers. So I just chose a random number to put in here to show you the problem. Same thing for the first one. So it's not necessarily a number that you had in your homework, but it's the same exact method to get to the answer. Those are the only two that I had for additional Chapter 9 review. But those were kind of the two hardest ones that we hadn't yet covered. I'll wait a few seconds and then we'll start the actual final exam review. If you have questions about the final, like the format or anything like that, you can feel free to ask, throughout. Just throw your hand up or put your question in the chat and I'll answer it. But we will talk about it at the very end. Right. So now we're at final exam review. And as I said earlier, this is a combination of problems from the final exam review that I posted and a couple of new questions. This one is directly from the final exam review. The answer is on there and the final equation is on there, but talking it through and writing out the plan, those are things that I typically don't include on the answer key. So if you want that kind of thing, come to these notes, which will be posted on Blackboard and you'll see the video. Or if you have more questions, try to set up a time with me as soon as possible. So let's get going on this one. How many milliliters of carbon dioxide gas at STP are produced from the decomposition of 1.75 grams sodium hydrogen carbonate? Clearly, this is a stoichiometry problem. This equation is balanced. One of the ways you can tell that an equation is balanced without actually going through and balancing it or checking it is if you see coefficients, like a 2 in front of something, chances are it's balanced. But to be on the safe side, I would encourage you to go ahead and check it just to be sure. Make sure that it's balanced on both sides. Now, I wrote the problem, so I know it's balanced. Let's see what we're actually trying to do here. We're starting with 1.75 grams of sodium hydrogen carbonate. We need to figure out how many milliliters of carbon dioxide at STP. We're starting with the mass, trying to find a volume. So it's a mass to volume question. Here's our plan. We use the grams of our starting material. We need to get to moles. That's always the first step. Wherever you're starting, get to moles. I'll write the molar masses up here so that it doesn't seem like it's coming out of the blue. So that's the molar mass for sodium hydrogen carbonate. We need to get to moles of carbon dioxide. Why am I writing molar mass? I don't know, because that's just where my brain wants to go. We don't need a molar mass. We need a mole-mole ratio. And it needs to be in the form of B over A. B is the compound that we're trying to figure out. We're trying to figure out how much we're making. That's the CO2. A is the one we've got some information on. So when we write that mole-mole ratio, it'll have the moles of carbon dioxide on the top from the chemical equation and the moles of sodium hydrogen carbonate on the bottom. Then we need to get to volume, which means molar volume at STP. But remember to look back at the problem. We need to figure out how many milliliters. If we stopped right here, we would be in liters. So I'll remind you of how to do that last part. That's a metric conversion from chapter 2. Now let's set it up. That will get us to moles of sodium hydrogen carbonate. Now we need to put that mole-mole ratio together. Only 1 mole of carbon dioxide. We've got 2 moles of the sodium hydrogen carbonate. From our unit equation, which is here, we need to have a unit factor. We're canceling out the moles of CO2, so 1 mole CO2 should go on the bottom, and the 22.4 liters should go at the top. But that gives us liters, not milliliters. In 1 liter, there are 1,000 milliliters. And that's something that you can get from the metric prefixes chart from chapter 2. Make sure that you brush up on those because you'll see it on the final. Double check your units. All right, so we're good here. That's how you put it into your calculator. And those parentheses help to keep certain things together. It just helps your calculator do things in the right order without having to think too much. When you put all that into your calculator, you should get 233 milliliters of carbon dioxide gas. I'll linger for a second. If you have any questions about this one, you can throw it in the chat. Otherwise, in about 10 seconds, I'll move on to the next problem. Next problem. This one is a new one. So you will not see this anywhere else. It may look suspiciously familiar, it may look a lot like the one that we just did, but there are some key differences here. Same equation. We're trying to figure out the number of milliliters of gas produced from 1.75 grams of sodium hydrogen carbonate. But we're not at STP. We're at a certain temperature, 65 degrees Celsius, and a certain pressure, 1.50 atmospheres. Whenever you're figuring out the volume of a gas and you don't see STP, and instead you see a temperature and a pressure, that should clue you in that you're going to have to use the ideal gas law if you're looking for a volume. So the first step is to figure out a mass to mole question. Pretty much you figure out if I have 1.75 grams of sodium hydrogen carbonate, how many moles of CO2 do I make? Then you take those moles and you use the ideal gas law. After you do that, the ideal gas law will give you units in liters. You have to then convert to milliliters, the same way we did in the last problem. So I'm not going to write out the plan again. It's the same thing for setting up how to go from the mass to the moles, but I will write out the equation. And that's where we stop. We end up with moles of carbon dioxide. So to put this into your calculator, it would be that. I'm carrying some extra digits here because we're not at the end of the problem. I don't want to round too early. That was the first part. Step 1. Step 2, we're using the ideal gas law. So this problem, again, great for a final exam. Why? Because you're encompassing 2 different chapters. So I'm testing a couple of different things with one question. I don't like to give super long finals. I want to try to give you maybe 10 regular questions, 1 or 2 extra credit, and then we're done. Shouldn't have to be 70 questions long. Okay. You got your stoichiometry problem and your gas law problem all in one. That's the ideal gas law. What we solved for was N. N is the number of moles of gas. We need to figure out the volume based on the conditions that we have. To isolate the volume, you divide by P. Now let's assign our variables. We know our N. R is the ideal gas constant. The temperature we were given in the problem, which is 65 degrees Celsius. But you need to convert that to Kelvin. Gas laws require Kelvin temperatures, not Celsius. So you add 273 to that, and you get 338 Kelvin. And our pressure was given at 1.50 atmospheres. Now we can substitute all of this in and get our answer. Now the units for the gas constant are a little bit weird, but they cancel out all of the units except for the one that you're interested in, and we care about the volume. When you're putting that into your calculator, that's going to get you where you need to go. Parentheses are always going to be your friends. So that's our answer, 0.193 liters. But we still have one more step. So if you stopped there, it would still be wrong. We've got to convert from liters to milliliters. So that is a combination of stoichiometry and the ideal gas law. You might see a question like this on your exam. I'll pause here for about 10 seconds, and if you have any questions, you can let me know. Otherwise, I'll move on. Then we'll keep it pushing. This one is from the final exam review that's posted, so the answer is there. But if you need a little extra help with walking it through, that's what we're going to do. If 1 gram of magnesium hydroxide reacts with 0.605 grams of sulfuric acid, what is the mass of magnesium sulfate produced? And then we have a second question. A student performed the experiment, resulting in 0.455 grams of magnesium sulfate being produced. What is the percent yield? Woof. That's a long question. I apologize. We've got an equation here. It is balanced. I'm not going to go through and show you that it is, but it is. But when you see something like this, make sure you go through and double check. Now, what type of problem is this? Well, we have two masses, and we're asked about a mass in that first question. So we're going from one mass to another mass. But it's a little bit more than that. There's also a limiting reactant flare to this question. If we mix these two things together, one of the ingredients is going to be in excess. The other one will be limiting. The one that's limiting will limit how much magnesium sulfate we produce. So we need to do two smaller mass-to-mass questions to figure out which one of our reactants is going to limit the amount of product we make. Once we figure that out, we'll know what our theoretical yield is. Which is required to calculate the percent yield. The actual yield is given in the problem. So when you see a student performed or somebody did an experiment resulting in blah, blah, blah being made, the blah, blah, blah is the actual yield. First up, we're going to write a plan. We're going to write a generic plan with A and B. That way we can fill it in with the magnesium hydroxide and with the sulfuric acid. Starting with grams of A, we get to moles of A using the molar mass. We get to moles of B using a mole-mole ratio of B over A. Then you use the molar mass of B to get you grams of B. So we have to do this type of problem twice. I'm going to write it out here for you. First up, the magnesium hydroxide. That's what we're starting with, 1 gram. We first have to convert to moles. So I didn't write up the molar masses on here, but that's what I'm writing here. It's coming kind of out of left field. I apologize. Then we have to use our mole-mole ratio. We're looking at magnesium sulfate. On the top, it's the one that we don't know about. And magnesium hydroxide is the one we do know something about. Again, this is a molar mass that I calculated earlier for magnesium sulfate. Double check your units. When you do all that math, you should get 2.06 grams of magnesium sulfate. Then we have to do all that again with the amount of sulfuric acid that we're given in the problem. So that will get us to moles of sulfuric acid. We still have the 1 mole of magnesium sulfate in the top because it's still the B in this equation. On the bottom, however, we've got sulfuric acid. This last one, where we're converting to grams, is going to be exactly the same. And that's because we're converting moles of magnesium sulfate to grams. So it's the same unit factor. Now we need to figure out which one of these we're actually going to make. So the question that we have to answer, and I'll write it in a different color. Which reactant makes the least product? Another way to say that is, which one of these numbers is smaller? 0.742 is definitely smaller than 2.06. So that's going to be our theoretical yield. We answered one question. Still need to figure out the percent yield. The actual yield you get from the problem, that's 0.455 grams. The theoretical yield is what we just calculated, 0.742 grams. Multiply that by 100. (61.3%) is your percent yield. So we'll pause here and take a lay of the land. How are we doing? Are these problems helpful? Is this format helpful, where I'm just running through problems and narrating them as you watch in amazement? How are we doing? Okay. I'm glad it's helpful, because if it's not, we should do something else. I'm here for y'all. And I know this is a lot, so hopefully this will be a resource. Yeah, and I know people like to write it down. If you miss something, don't worry, because the notes will be up too. So you can always fill in the blanks later. And if I'm like, okay, next slide, and you're not ready, always, wave me down. Hey. And I'll pause for you. But that's partially why I pause for a few seconds after each problem anyway. So we've been in stoichiometry land for quite some time. And I don't know about you, but I'm ready to move on. So now we'll go to gas law land, and we'll be there for a little while. This problem is from the final exam review. So the answer is there, but I'll talk you through kind of how you get to it. We've got a sample of oxygen gas, and it occupies this volume at this pressure at this temperature. We have to figure out the mass of the sample. So let's write down what we know. We've got a volume of 855 milliliters, a pressure at 710 millimeters of mercury, and a temperature of 155 degrees Celsius. We have to figure out the mass of the sample. Well, let's think about this. I've got pressure, volume, and temperature. I've only got one bit of information for each of these. I don't have a T1 and a T2 or a P1 and a P2. I've just got one of each. I'm also asked about the mass. The only gas law that deals with one of each of these variables and can give you some information that's linked to the mass of a sample is the ideal gas law. And the reason is it uses moles. So the plan is to first use the ideal gas law to solve for N, which will tell us the number of moles. Then we can use the molar mass of oxygen gas, which remember is O2, to calculate the grams, which is the mass. Before we get there, we've got to do a little bit more work. Gas laws require Kelvin temperatures. To do that, you have to add 273 degrees. Well, not degrees, it's just 273. So there's a temperature. The R constant that we use the units are liter atmospheres per mole Kelvin. Our pressure is in millimeters of mercury. We can't use that directly in the ideal gas law with this gas constant. So you have to convert from millimeters of mercury to atmospheres. The final exam is take home, so that means open note. You'll have access to all the things just like you would if you're doing homework. So you'd look up that units of pressure table from chapter 10 and find how many millimeters of mercury equal 1 atmosphere. It's in the table. I'm carrying some extra digits here just because we're not rounding yet. So I don't want to influence my answer too much. We also have to convert our volume. We have milliliters. We need liters for the ideal gas law. We have to divide by 1,000. The ideal gas law requires a lot more work if you don't have the right units. The other gas laws, they don't care about units. As long as the pressures match, the volumes match, and you have temperature in Kelvin, you're good to go. Ideal gas law, you have to make sure that your units match the units of your gas law constant. Now that we've done all that leg work, we can actually go ahead and rearrange the equation to solve for n. So we put the pressure times the volume over top, and then R times T on the bottom. We'll fill it in. Make sure to use parentheses just to make sure that you get the desired outcome from your calculator. So when we do all of this math, we should end up with the number of moles. So that was all step 1. We solved for n. Now we've got to use it to figure out the number of grams of oxygen that we have. Again, remember that oxygen gas is O2, which means that the molar mass is going to be whatever it says on the periodic table for oxygen times 2. If you use the wrong molar mass, you'll get the wrong mass of oxygen at the end. And there's our mass, 0.727 grams of oxygen. One of the things that will help you with the final exam is seeing that you can connect different concepts either within a chapter or concepts that span chapters. So we used the ideal gas law, which was chapter 10, but we also went back to chapter 8 to connect the number of moles to the mass of the sample. We'll move on to the next question. And if you need to take a break, you can. This is a lot. I'm going to keep trucking through. The video will be up on YouTube. The notes will be there. So if you just need to walk a lap in your room or wherever you're logged in virtually, go ahead. That's all right. Just shake it off. Come back. This here is another new question. If we have 1.25 moles of helium gas, it occupies 5 liters, 2.25 atmospheres. What is the temperature in Kelvin? Let's write down what we know. We've got number of moles. we have a volume in liters, a pressure, and it's in atmospheres. We need to figure out what the temperature is in Kelvin. The only gas law that we've covered that talks about moles is the ideal gas law. The only thing that we're not given here is the R value, which is a constant. This is a straightforward gas law problem. This time we're solving for temperature. Substitute all the values that you have. Remembering that parentheses are your friends. So when I place them in the problem, I place them meaningfully. The only unit left in our gas law constant is Kelvin. And there's our answer. Now this answer has 3 sig figs because of that decimal place, or the decimal point. Notice that each of our pieces of information have 3 sig figs. So make sure that you report your answer using the same number. More gas laws. This one is also new. Let's read through the problem. What volume in liters is occupied by 3.38 times 10 to the 22nd nitrogen molecules at 100 degrees Celsius and 255 millimeters of mercury? We're asked about a volume in liters. We're going to skip over the molecules for a second and get down the other information. Temperature, and a pressure. We're also given the number of molecules. The number of molecules can be linked to a mass, or it could be linked to moles. And since we're doing gas laws, we've only got one set of information, one pressure, one temperature, we're looking for a volume, and we're told the number of molecules. That means we should use the ideal gas law. So the first step in this is going to be taking the number of molecules and converting to moles. Then use the ideal gas law. And we'll solve for volume. So first things first. I'll do this step in purple. We need to figure out how many moles there are. What links us is Avogadro's number. So that's what we have to use to get from molecules to moles. This is another Chapter 8 concept. When you're putting this into your calculator, I suggest using parentheses around your scientific notation just to make sure that everything is okie doke. Make sure that your scientific notation, that the exponents won't do anything weird, the coefficient won't do anything weird. Calculators are helpful, but you have to be very exact with what you want. We'll do the second part in blue. The ideal gas law, again, PV equals nRT. The R is a constant. We have to solve for V. Divide both sides by P. Then you put in all of the things that you know. Now, we've got a temperature in degrees Celsius, and we have a pressure in millimeters of mercury. So we've got to convert those. (373 Kelvin), because you just add 273. For the pressure, again, we have to convert. Now that we've done our conversions, we can carry on with putting in all of our numbers. So the moles we calculated, R is the constant, and we have our temperature. Divide all of that by the pressure. what we're going to be left with is the number of liters. And when you do all this in your calculator, you should get 5.12 liters. Next problem. This is our last stop in gas law land. We'll move on to do a couple of problems outside of chapters 9 and 10, which, remember, the final is going to focus on chapters 9 and 10. That's why I focused the review on problems in those areas. We've got calcium metal and water producing hydrogen gas. And if the volume of wet gas collected over water is 95 milliliters at 20 degrees Celsius, and at this pressure, what is the volume of dry gas at STP? And there's a hint saying that the vapor pressure of water is 20 degrees Celsius, or at 20 degrees Celsius, is 17.5 millimeters of mercury. It's a pretty big paragraph, but let's distill it down. We're told a volume of 95 milliliters, a temperature of 20 degrees Celsius, and a pressure of 758 millimeters of mercury. We're asked about the volume of dry gas at STP conditions. Well, STP means that you're at 273 Kelvin and 1 atmosphere, which is the same as 760 millimeters of mercury. So it sounds like we actually have two sets of conditions here. We don't know what the volume is. T2 we know it's 273. And our pressure is 760 millimeters of mercury. But we haven't addressed the fact that we were told the volume of wet gas and the pressure of the wet gas. Wet gas means that this is the pressure of the water vapor plus the pressure of the hydrogen gas. The pressure that we're given, the volume of dry gas at STP, that pressure is just the pressure of the hydrogen gas. So we need to get rid of the pressure from the water. That's where Dalton's law of partial pressures comes in. We're going to use that law to find the pressure of just the hydrogen gas alone. We're told the contribution of the water vapor. So that means we just have to subtract that off. So that is our actual P1. Second step is figure out which gas law to use for this. We use Dalton's law of partial pressures, but we still haven't arrived at the answer of what the new volume is. We've got a pressure, temperature, and a volume, and we've got an initial set and a final set of information. That's the combined gas law. You have to cross multiply first to make this usable. We're solving for V2, and I like to circle it just to keep me grounded. There's a lot of letters there. Don't want to get confused. We're going to divide both sides by P2 T1. Let's rewrite the expression. We've got V2 on one side. We can pull out V1. So that's the equation that we end up with. We put in our numbers. And be careful here. Make sure that you're putting in the right number in the right location. If you switch P1 and P2, you'll get a different answer, and that different answer is wrong. I like parentheses. You should know that by now. Our temperature, our initial one is in Celsius. We need to convert to Kelvin. So you add 273. When you do this math, you should get 86.2 milliliters. All gas laws, but we had to combine a couple of them to get to the answer. That's kind of the theme for the final exam. Since it's take home and it is cumulative, meaning it covers all the content that we've covered, you're going to see slightly more complicated problems, but if you take the time to break them down and figure out, okay, what are the smaller questions in here that I need to answer, it'll make it seem much more approachable and you'll do a lot better. Now we're going to do a couple of problems that are kind of outside of chapters 9 and 10. We're going to hit back to chapter 2 with the metric prefixes. There's a chart with the metric prefixes in the chapter 2 notes. You'll need that for this question and any other one like it on the exam. How many nanograms are in 650 milligrams? When you rephrase the question and you see a prefix on both sides, that means that you can't directly convert from milligrams to nanograms. We've got to use grams as a go-between. So the first thing we do is convert milligrams to grams. Then we convert those grams into nanograms. You go to the metric prefixes chart to get the unit equation. And this is just one way to write this unit equation. You can write it another way, which I'm not going to go into. I'll just show you the one way. If this confuses you, then you can ask me about the other way. Then you write the unit factors. We're going to do the same thing for the second half of the equation. We're trying to go from grams to nanograms. If I have 1 gram, then that is going to be equal to 1 times 10 to the 9th nanograms. Then I write out my unit factors just like before. Then we set up the actual question. I'm trying to go from milligrams to grams to nanograms. Since milligrams are in the numerator, I need milligrams in the denominator of the unit factor. I need to do the same thing, only I'm going from grams to nanograms this time. I want to get rid of grams, so they should be in the bottom of the unit factor. Make sure that your units check out. And then you do the calculation. Make sure that you brush up on these. Remember that there's practice problems for these chapters already posted with answer keys. So you can do a few problems to kind of jog your memory if you go through the final exam review and you're like, oh man, I did not get this one. Then you can find similar problems. This is the last question that we're going to do for exam review. What's the density of propane gas at STP? We went over density in Chapter 8, and for gases at STP, you can take the molar mass of your gas and divide it by the molar volume. Molar volume, remember, what that means is 1 mole of gas. It has a volume of 22.4 liters. So we're going to use this number for molar volume. We need to figure out the molar mass of propane. There are 3 carbons and there are 8 hydrogens. You add those together and that's the molar mass. That's what you use in the density equation. Then you put in molar volume at the bottom. You do the division and you get 1.99 grams per liter. Don't forget your units. Grams per liter are the units for gas density. So when you're reporting units for gas density, make sure it's grams per liter. That's it. You're going to have a take-home final that is due on Monday, May 3rd by 11:59 p.m. It's take-home, which means you have access to your notes. Use them. You will write out your answers, with all your work, just like you do for the chapter check-ins. And then submit a PDF like you would for a chapter check-in, only it's the final exam. You've got Mastering Chemistry Chapter 10 assignments due on Sunday. So don't forget about Chapter 10. I know we've been focusing a lot of our efforts on Chapter 9, but don't let Chapter 10 slip by. That's due on Sunday. You also have the Chemistry Primer, which you can work on up through the end of Wednesday, May 5th. That is extra credit. Whatever you finish will be added to your Mastering Chemistry score, and that will definitely help boost your grade. It's also helpful to use it to study because it covers all the topics that we went over. So you can study and get some extra credit at the same time. With that, we're done. If you have any questions about the exam, you can stick around and ask them. Otherwise, you're free to go. I'll stick around for maybe until about 3:45 if you have another quick question to pop in. Otherwise, have a great day and good luck.